Okay, so moving on, this is the last piece of information that we will cover in this class. So if you're listening to this and you're coming to the tail end of Math 105, then congratulations. You've made it through the course. What we're going to talk about is defects in voting methods. We talked about 4 voting methods in the previous lecture. We talked about the plurality method, which was, whoever wins the most votes wins the election. We talked about the board account method, where you rank all of the individuals on the ballot, and first place, or each person gets a different number of points depending on their rank, okay? And the person with the highest number of points wins the election. We talked about plurality with elimination. This is where, again, you rank everybody on the ballot, and if nobody has 50% of the, if none of the first place candidates has 50%, more than 50% of the vote, then you eliminate the person with the least number of votes and sort of run the election again. And you keep doing that until you get somebody who wins more than 50% of the vote. And then we talked about the pairwise comparison method, which is where you sort of simulate doing a bunch of elections. If there are multiple people in the election, then you simulate doing head-to-head races with each pair of people in the election. So go back and watch lecture 35 if you haven't done so already. Otherwise, this lecture might not make a ton of sense to you. But the question is, of those 4 methods, which one is best? And answering that question is difficult. What we want is a fair election, right? Ultimately, that's what we want. And we're going to determine how fair an election is based on the following 4 criteria. So we call these the 4 fairness criteria. The first one is the majority criterion. And actually, I say the first one, but we're not going to cover these in this order, but we will cover all 4 of these in this lecture. So we're going to talk about the majority criterion, Condorcet's criterion, the independence of irrelevant alternatives criterion, which I might call the IIA for short, right? The IIA criterion, and then the monotonicity criterion. So let's start off by talking about the majority criterion. So it's pretty straightforward. The majority criterion says that if a majority of the votes, of the voters, in other words, more than half, rank a candidate as their first choice, then that candidate should win the election. Okay? That's obvious, right? So if more than half of people rank some candidate as their first choice, that candidate should win. The plurality method, the plurality with elimination method, and the pairwise comparison method, all 3 of those methods always satisfy this criterion. However, the board account method sometimes fails to meet this criterion, and we can see that in the next example. So this one says, Motor Tendency magazine has narrowed down its choice for car of the year to the following 4 cars: the Audi R8, the BMW Z4, the Corvette Zora ZR1, and the Dodge Viper. I know nothing about cars, by the way. For me, if it runs, if it gets me from A to B, then it's a good car. Anyway, a 3-person editorial panel using the board account method will make the final selection. Preference ballots for the panel members are as shown. So the first person on the selection panel rated the Corvette first, the Dodge Viper second, the Audi third, and the BMW fourth. The next person rated the Corvette first, the Dodge second, the BMW third, and the Audi fourth. And then the third person did the Dodge first, the Audi. Okay, so you get the idea. So let's determine the winner. Now, first of all, we should say that the Corvette won the majority. The Corvette won 2 out of 3, right? So that's 66.6%, right? So Corvette is the clear winner. But they said that they would use the board account method to determine the winner. So let's see, using the board account method, who the winner is, and then it's going to turn out that this violates the majority criterion, because the majority criterion says that the Corvette should be the winner, but we'll see if we use the board account method who ends up coming out on top. So Okay, so again, I'm going to arrange my work into a chart. We've got the Audi, the BMW, and the Corvette. The Audi was ranked first a couple times. Actually, maybe never. It actually wasn't ever, but that's okay. We still need a column for first. It was ranked second. It was ranked third, and then we need the total number of points. Okay, so for the Audi, it was ranked first 0 times. In this case, oh, we have a Dodge Viper as well. I was like, why is it saying first, second, third, fourth? Okay, so sorry. So we also have a Dodge Viper. Okay, so but the Audi was ranked first 0 times. First place, since there are 4 people in the race, or 4 cars in the race, first place is worth 4 points. It was ranked second place once. Second place is worth 3 points. It was ranked third place once. Third place is worth 2 points. And it was worth, I need another column, don't I? Fourth place, and then we'll do total. It was ranked fourth place once, and that's worth 1 point. Oh, so this comes out to 0, 3, 2, 1. So that's 6. So the Audi got 6 points in total. What about the BMW? So the BMW got first place 0 times, got second place 0 times, got third place twice, and third place is worth 2 points. And then it got fourth place once. Fourth place is worth 1 point. So BMW earned 5 points in total. What about the Corvette? Corvette won first place twice. It won second place 0 times. It won third place 0 times. And it won fourth place once. So that's a total of 9 points for the Corvette. And then finally for the Dodge, it won first place once, second place twice, third place 0 times, and fourth place 0 times. So that totals to 10 points. So the Dodge won 10 points. Ooh, that's interesting, right? So even though the Corvette got the majority of first place votes, and therefore the Corvette should be the winner according to the Majority Criterion, the border count method will show us that Dodge is the winner, right? So according to border count, Dodge wins. Ugh, I missed a D. Dodge wins. But according to the Majority Criterion, the Corvette should have won. Okay, so the border count violates the Majority Criterion. Okay, so benefits of the border count are that you can label your second, third, and fourth choices and stuff. So if you have a person who wins by a narrow margin, like if you don't have somebody who wins the majority, and we saw that, by the way, in the previous lecture, right? So Kareem won the election because he had 11 votes. He had more votes than anyone else. But he didn't have the majority. He only had 11 out of 33, which is 33%, right? So when you have this situation, border count is kind of a nice thing. But the problem is that border count could make it so that if you do have a majority, the majority doesn't win the election, which is kind of strange, right? Okay, so that's the problem with border count. Let's talk next about the monotonicity criterion. This one is a little bit strange to wrap your brain around at first, but hopefully it'll make some sense to you. So the monotonicity criterion says that if X wins an election, and in a re-election all voters who change their votes only change their votes to favor X, then X also wins the re-election. So, in other words, if X is the winner in the first election, and then X becomes even more popular, then X should also win the re-election. Okay? So that seems like a pretty common sense thing, right? If you won an election and then you become more popular, you should definitely win the re-election then, right? The plurality method, the border count method, and the pairwise comparison method always satisfy the monotonicity criterion. However, the plurality with elimination method can sometimes violate this criterion, as we'll see in the next example. So let's take a look. Okay. So the preference ballots for the president of the International Students Organization, in which Michael Chang, Rukevwe Kwame, and Anna Wojtek are candidates, are summarized below. Okay. So 6 people cast their ballots this way, 6 people cast their ballots this way, and 5 people cast their ballots this way. It says use the plurality with elimination method to determine the winner. Okay, so remember the plurality with elimination method means that if nobody wins the majority, then we have to eliminate the last place winner and then run a new election, which we can simulate doing since the ballots have ranked the candidates already. So let's see. So C wins 6 votes, K wins 6 votes, W wins 5 votes. That means that there were 6 plus 6 is 12, plus 5 is 17, so 17 votes in total. So first of all, C and K are tied, but second of all, 6 out of 17 is not more than 50%, right? So C got 6, K got 6, W got 5. And since neither of these are the majority, or since none of these are the majority, we eliminate the last place. So we're going to eliminate all of the W's. And then I'm going to make a new chart. So 6, 6, 5. And this first one's going to be C, K. The next one's going to be K, C. And the last one's going to be C, K. So now, let's see. So now C would have 6 plus 5 is 11 votes, and K would only have 6. So C is the winner. All right, so Michael Chang wins. Okay. Now suppose that the day before the election, okay, so we're kind of going back in time or whatever, and we're pretending that the day before the election, 2 of the voters who prefer Kwame hear of some important information that causes Chang to become their favorite. So they change their votes, right? So before you had this situation where you had 6 people who voted for Kwame, or who voted KWC, but 2 of these people hear some information that makes Chang their favorite, and so they change from this to this, right? So now you have 4 people casting their votes this way because you lost 2 of them, and you have 8 people casting their votes this way because you gained 2 here, right? So in other words, Chang has become a lot more popular, okay? So Chang has become a lot more popular, and since Chang won the first time around, since he's become more popular now, you would expect him to win the second time around. Let's see if that happens. So first of all, note that Chang got 8 out of how many votes? So this is 8 plus 4 is 12, 17. 8 out of 17 is not quite 50%. Yeah, that's like 47%. Right? The other 2 are even less, right? K got 4 out of 17, which is like 23.5%. And W got 5 out of 17, which is about 29.4%. Okay, so none of them have the majority, right? None of them have at least 50%. So what do? We have to get rid of the person with the least number of votes, which in this case is going to be K. All right, and so we get rid of K here, here, and here, and then make a new chart. And the new chart's going to look like this. So we ignore the K's and we have C, W, W, C, W, C. So now Chang still has 8 out of 17 votes, but W has 9 out of 17 votes. 9 out of 17 is a slight majority. 9 out of 17 is about 53%, right? So this is about 53%. This one is about 47%. So W wins. Who was W? It was Anna Wojtek. Okay. So note the paradox here. Chang lost the election even though he was more popular than when he won the first time. Right? So up here he won when he was less popular. And here he lost even though he was more popular. So that's strange, right? That's a very strange thing. So monotonicity criterion requires that doesn't happen. And the plurality with elimination method can sometimes violate that monotonicity criterion. So that's kind of a drawback of plurality with elimination. There are some countries that use like a plurality with elimination method, especially if they have a lot of political parties. Like in the US, we only have 2 major political parties. There are others, but there are 2 major ones. In other countries, they might have 5 or 6 major political parties, and so they'll use plurality with elimination oftentimes to determine winners to those kinds of things. Anyway, moving on. So let's talk about Condorcet's criterion. Condorcet's criterion says that if candidate X can defeat each of the other candidates in a head-to-head vote, then X is the winner of the election. Okay. Now, the pairwise comparison method of voting was devised explicitly to meet Condorcet's criterion. So the pairwise comparison method definitely meets this criterion. However, none of the other 3 voting methods meet Condorcet's criterion. So, and in the following example, we'll show how the plurality method can sometimes violate Condorcet's criterion. The fact of the matter is that it's not just the plurality method that fails to meet this criterion. It's the plurality with elimination, and it's the what was the other one? And it's the board account method. So board account and plurality with elimination also fail to meet Condorcet's criterion. But I'm not going to show you an example of each of those. I'm just going to show you how the plurality method can sometimes violate Condorcet's criterion. So let's take a look. So this one says, a 7-member Olympic committee is voting using preference ballots to decide which one of Hungary, India, and Taiwan will remain as a finalist country to host the 2024 Olympics. I don't know. I mean, your book is a little bit out of date, so not your book. The book that I drew this example from is a little bit out of date, so I'm not sure if this has already been decided. It probably has, but anyway, the Olympic Committee is voting using preference ballots to determine which one of Hungary, India, and Taiwan will remain as a finalist country to host the 2024 Olympics. The partially completed preference ballots are as follows. So for first place, 3 people voted for Hungary, 2 for India, and 2 for Taiwan. With the plurality voting method, Hungary is the winner. Okay. However, it's possible that in head-to-head races, either India or Taiwan could be the winner. So let's complete the ballot. So we're going to work backwards, but let's complete the ballot so that in head-to-head voting, India defeats both Hungary and Taiwan. In other words, we want to give an example of a voting outcome in which Condorcet's criterion is not satisfied. And that'll show that the plurality voting method does not always satisfy Condorcet's criterion. Well, let's see. So for these head-to-head races, let's see if we can think this through. If we want India to defeat both Hungary and Taiwan, then we need for India to come before Hungary. So India cannot come before Hungary here, right? But India could come before Hungary in these two columns. In fact, it has to. And then it could also come before Hungary in these two columns. The way that it would come before Hungary in these two columns is if we put I in both of these places and H in both of these places. So now in a head-to-head race, Hungary's going to win in these three columns, India's going to win in these two columns, and India's also going to win in these two columns. In fact, it doesn't even matter. We could put Taiwan here and Hungary here, and it doesn't matter. India's going to come before Taiwan and Hungary in both of those columns. So already we can see that in a head-to-head race, Hungary's going to beat out India in these three columns, but India is going to beat out Hungary in these four columns. So India is going to beat Hungary in a head-to-head race. Okay. We also want India to defeat Taiwan. Okay. So here India is going to lose to Taiwan, but here India is going to defeat Taiwan. And to make India defeat Taiwan here, all we have to do is put India, Taiwan, India, Taiwan. Here we could switch it up and put Taiwan, India. It doesn't matter because we already have India before Taiwan in 1, 2, 3, 4 columns, and Taiwan would be before India in 2 columns. So this third one doesn't matter. You could put it either way. But just for the sake of argument, I'm going to put it like this. Okay. So if we fill it out this way, now we can check our work, right? If we do a head-to-head race between Hungary and India, Hungary's going to win 1, 2, 3 times, and India's going to win 1, 2, 3, 4 times. So India wins. And if we do a head-to-head race against India and Taiwan, India is going to win in 1, 2, 3, 4, 5 cases, and Taiwan is going to win in 2 cases. So again, India is the winner. So in a head-to-head voting system, if this was the outcome of the election, then in a head-to-head voting system, India would win both times. But if you just use the plurality method, where only people's first choice counts, Hungary is declared the winner. So that's kind of a problem. So in other words, if there were only 2 candidates, in either India and Hungary or India and Taiwan, then India would win in either case. Yet when all 3 of them run in a single race, Hungary comes out as the winner. And so the simple plurality voting sometimes fails Condorcet's criterion. Okay? All right. So far, the pairwise comparison method is the only one that has satisfied all of the criteria that we've studied. So you might think, well, the pairwise comparison method is the best one. But let's not celebrate quite yet. Because the last one, the IIA criterion, the independence of irrelevant alternatives criterion, states that if candidate X wins an election, some non-winners are removed from the ballot, and then a recount is done, then X should still win the election. Okay? So if X is the winner, then when you remove some non-winners from the ballot, X should still come out as the winner. turns out that none of the 4 voting methods we've discussed can always be counted on to satisfy this criterion. Okay, and I'm going to specifically show you how, because the pairwise comparison passes the other 3 criteria, I'm going to specifically show you how the pairwise comparison method violates the independence of an irrelevant alternatives criterion by taking a look at this example. Okay, so this one says, the 18-member board of the Universal Cheerleaders Association is using the pairwise comparison method to choose where to hold the next college nationals competition. The places being considered are Atlanta, Boston, Cleveland, and Disney World, which I guess would be Orlando, but they wanted to keep A, B, C, D. The following table summarizes the preference ballots cast for A, B, C, and D. Okay. Using the pairwise comparison method, who is the winner of this election? And then, if any of the losing candidates are removed, does this change the results of the election? Well, let's see. So using a pairwise comparison, we need to compare A, and we need to make 6 comparisons. We need to compare A and B, A and C, A and D, B and C, B and D, and then C and D. Okay. And then it's fine. Okay, so let's see. If we're comparing A and B, A wins here, A wins here, B wins here, and A wins here. So we get A, B, A. So how many points does A get? 8 plus 4 is 12, plus 1 more is 13. And B would just get 5. So in a head-to-head race, A wins. What about A and C? Here, A would win, C would win. And A would win again. Also, this is the same scenario. A would win 13 votes, and C would win 5 votes. So A would win in the head-to-head race there. What if we compare A and D? A wins, D wins. D wins here, D wins, and D wins. So A gets 8 votes, and D gets 4 plus 5 is 9, plus 1 is 10. So D gets 10 votes. So D would win in that head-to-head race. Okay. Let's compare B and C. Okay. Here B wins, here C wins, here C wins, and here B wins. So B would get how many? 8 plus 1 is 9 votes. C would get 4 plus 5, which is also 9 votes. So this is a tie. Let's compare B and D. Here B would win, here D would win, here B would win, and here D would win. So B gets 8 plus 5 is 13 votes, and D gets 5 votes. So B would win. And then if we compare C and D, here C would win, here D would win, C would win, and D would win. So C gets 8 plus 5 is 13, and D gets 4 plus 1 is 5. So here C would win. Okay, so who's the overall winner? Well, I'm going to make my little table. So I'm going to say candidate, and then points. It looks like A gets 2 points, B gets 1.5 points, C gets 1.5 points, and D gets 1 point. So A would be declared the winner. Even though A doesn't win in all of the head-to-head matches, right? A loses against D, but it still has more points, so A is the winner. So Atlanta wins. Atlanta wins. Okay, but that's just half of it. So that's using the pairwise comparison method. Atlanta wins. So this is the pairwise result. Okay, but then it says, if any of the losing candidates are removed, does this change the results of the election? In other words, if we eliminate one of the losers, either B, C, or D, does this make it so that we get a different winner? So let's see. Who should we remove to try to get a different outcome? Maybe we can remove a couple of people, actually, because we can remove more than one loser. So I'm looking at the chart here. If we eliminate D, then A just gets more votes, so that's not going to help. We probably shouldn't eliminate D. If we eliminate C, B would get some more. If we also eliminate B, then D gets a lot more. So let's eliminate B and C just to see what happens. So if I eliminate B and C everywhere. I should have done that in pencil in case it was a bad choice, but what table do I get now? 8, 4, 5, 1. And I would have A, D, D, A, D, A, D, A. Yeah, I bet that this is going to come out very differently now, right? Because now you can see in a head-to-head race, A is going to get 8 votes and D is going to get 9, 10 votes, right? So if we remove B and C, then A loses against D. And I guess we knew that already, right? We knew that already. A loses against D in a head-to-head. So that's interesting, right? Because A won using the pairwise comparison method. Atlanta won. And so you would expect Atlanta to win if you remove some losers. And yet here we removed some losers, and that caused Atlanta also to lose, right? We removed some losers, and that caused suddenly for Disney World to be the winner. So, so that shows that the pairwise comparison method fails to satisfy the IIA criterion, the independence of irrelevant alternatives criterion. So what does this mean, right? So to summarize, right? Here we have the voting methods, and here we have the fairness criteria, okay? And a yes means that the voting method satisfies the criterion. A no means that the voting method does not satisfy the criterion. So the simple majority method these are the these are the fairness criteria, and these are the voting methods. So the plurality method satisfies the majority criterion. The border count does not. Plurality with elimination does. Pairwise comparison does. The plurality method does not satisfy Condorcet. Neither does the border count. Neither does plurality with elimination, but pairwise comparison does. None of them satisfy, I don't know why I called it the IRA. It should be called the IIA. Right? None of them satisfies the independence of irrelevant alternatives criterion. None of them satisfy that one. And then the monotonicity requirement, plurality, border count, and pairwise comparison can meet that criterion, but plurality with elimination does not. So this begs the question, right? Is there any election system that is totally fair? Is there any election system that will meet all four of these fairness criteria? And the answer is no. This is known as Ariel's Impossibility Theorem. And Ariel's Impossibility Theorem says, in any election involving more than two candidates, there is no voting method that will satisfy all of the four fairness criteria. So mathematically speaking, no election system is totally fair. So, is that a reason to kind of throw up your hands and say, well, nothing is fair, and just kind of be nihilistic? I mean, the answer is no. We can still make things as fair as possible, but you're never going to have a totally perfect utopian fair system, okay? But we can make things as fair as possible, and all four of the voting systems that we've talked about are useful in different scenarios, right? So when you're determining which voting system to use, you just have to decide which fairness criteria are most important in that particular situation that you're faced with, okay? So they all have some benefits and drawbacks, and anyway, now you know a little bit more about each of them. So that's all I have to say about voting.